Hello guys, I hope you all are doing good. I am Vaishali Kikan, Assistant Professor Electronics and Communication Engineering Department at KIT Group of Institutions. So today in this session we are going to talk about the endpoint antenna array. I hope you all have seen the previous video in which we have already discussed about the 2-point antenna array with varying phase between the two antennas. I hope you have simulated the result. If not, it is highly recommended that you go back and watch the previous video once and then come to this video. So today we are going to talk about the endpoint antenna array, in which I am going to take the 5-point antenna array. So how we were going to make the antennas? I am going to make the 5 antennas with the help of the wire antennas. So I am clicking on the wire. This kind of window is going to open. So point 1 is 0, 0, minus 100, point 2 is 0, 0, 100. Okay, diameter is 1, material is copper. I am going to click OK. So this is how I am getting my wire 1. Again I am going to click on the wire. Now I am going to locate it at 200, 0, minus 100, 200, 0, 100. Diameter is 1, material is copper. Okay, so now I am going to take the next wire. I am going to locate it as minus 200, 0, minus 100, minus 200, 0, 100. I am going to click OK. This is how I got the third wire. Now I am going to click the 400, 0, minus 100, 400, 0, 100. So this is how I got the fourth wire. Again I am going to click minus 400, 0, minus 100, minus 400, 0, 100. Diameter is 1, material is copper, and this is how I got the 5 wires. Okay, so you can see we have the different wires, 5 different wires over here. Okay, you are not able to see it properly. I am going to take the diameter to be 3. Okay, now it is visible. Similarly, I am going to change the diameter of all of the wires so that it is properly visible to you. Okay, you can see we have the 5 wires over here. Now I am going to take a current source on each of the wire. So I am going to take current sources and I am going to place it on all of the wires. Now I am going to set the location at the center of all of the wire for the current sources. So from here also I can go to the design. From design I am going to the excitation, and then to the current source I am going to change the values. So now you can set the location to the minus 400, 0 and 0. Amplitude is 1, phase is 0. I am not changing the phase. I am taking the phase of all of the sources to be 0 only. Okay, so okay, here I have the minus 200, 0 and 0. Again amplitude is 1, phase is 0. Here also I am going to take the x, y, z to be 0, 0, 0. Amplitude is 1, phase is 0. Okay, here I am going to take 200, 0, 0 to place the source at the center. Amplitude is 1, phase is 0. Here also I am going to take it as 400, 0, 0. Okay, so amplitude is 1, phase is 0. So this is how I have made my 5-point antenna array. Now I am going to simulate it. Okay, I am taking just 1 point. I am going to simulate it. So now my simulation is over. I am going to see the radiation pattern. So if you remember the radiation pattern of the 2-point antenna array, the radiation pattern was having the lesser gain and the lesser directivity than the 5-point antenna array. So you can play the animations. You can see this is how my radiation would be looking like. This is my, if I click W, it is going to show me the wire as well. So you can see the directivity has highly increased. This is my radiation pattern for 5-point antenna array. I can go and I can click on the polar plot as well. So this is how I will be getting the polar plot. You can see this is how I will be having highly directional radiation pattern, right? So now I am going to change the phase. So here I am taking the alternate phases. So I am taking the phase of these two antennas to be 180 degree, and again I am going to simulate it, and then I am going to observe the radiation patterns once again. So you can see the radiation pattern is broadside now. So you can see the radiation pattern has changed to the broadside if I am changing the phase of the antennas. Okay, so you can also play with the phase, you can change the radiation pattern, you can click on the W option so that the wires would be visible, right? You can go and click on the polar plot so that the polar plot is visible. You can see this is how I will be having the polar plot. Okay, so now I am going to show you that how you can make the radiation pattern of 7-point antenna array. So here you are going to click one more wire. Okay, so I am going to take the wire at 600, 0 and minus 100, point 2 at 600, 0 and 100. I am going to click OK. Again I am going to take one more point. It is at minus 600, 0, minus 100, minus 600, 0, 100, and diameter was 3. Okay, so here also I have to change the diameter should be 3. Okay, so I am going to place the current source. Okay, so now you can observe how the radiation pattern would change if I change the number of antennas. So I am going to change the phase. I am going to put the phase 0. Here also I am going to put the phase 0, so that you will observe that if I am changing the number of elements, how the radiation pattern will become more directional. Okay, you can save the results and you can compare it later on as well, but I am going to show you on screen that how the radiation pattern will become more directional. So I am taking the point to be at 600, 0 and 0, amplitude is 1, phase is 0. Okay, so this is how I have made the 7-point antenna array. I am going to simulate it, and now we will be observing the results, the radiation pattern. So you can see the radiation pattern is become more directional. Now I can delete the wires. Okay, so I have deleted these two wires. I have deleted the two current sources as well. Okay, so now I have these wires only. I am going to simulate it again. Okay, so now I have 5 wires, 5 current sources. I am going to show you how the results would be different if I am going to increase the number of elements. So you can see I have these two radiation pattern. This was the radiation pattern when I had the 7-point antennas. This is the radiation pattern when I have the 5-point antenna. The maximum value is 1.070E01. Okay, here we have 1.505E01. Okay, so you can see I have the more maximum value over here, and we have the less maximum value over here. Okay, so you can see the minimum value also. Here we have the higher minimum value, and here we have the lower minimum value. This is how we will be changing the gain and the directivity if I am changing the number of elements in the radiation pattern, right? So I hope this thing is clear. So we are going to observe the theory part of n-point uniform antenna array. We have made the n-element antenna array and we have observed the radiation pattern for both end-fire and the broadside array with the help of the current sources. I have changed the phase angle of the source to achieve the directional pattern. We have observed the half wave dipole antenna at the frequency 75 megahertz, and we have the same dipoles that we had designed earlier. I hope you remember how we designed the previous dipole antennas, right? So the distance parameter was 25 to 400 degree with the step of 15 degree and the default 0 degree. You can also play with it. You can find out the frequency sweep was 25 to 500 megahertz with 11 point. I had taken only 1 point because we were not observing the near field. So this is how we will be having the radiation pattern. These are the grating lobes that are present. Okay, so grating lobes are non-intentional, right? So these are actually wasting some amount of power that was not desired. Okay, so this is how I had made the 5-point antenna array and the radiation patterns were looking like this. Okay, so you can change the distance, you can change the phase, and you can observe the radiation pattern. Okay, so coming to the theory part. Okay, here we have n-point antenna array which are kept at d distance apart. The distance d is equal in between all of the antennas, and also the electric field is same. So E1 is equal to E2 is equal to E3 up to En is equal to E0. Now if I observe the reference here at the antenna 1, antenna N is leading the most. The radiations from antenna N will be reaching the point P fastest, then antenna N minus 1, then antenna N minus 2, 4, 3, 2, 1. Antenna 1 is lagging. So now if I want to compute the path difference, it will be proportional to the d cos of phi plus alpha. If I remove the proportionality constant, it will be beta d cos of phi. If I want to find out the path difference between reference and antenna 3, it would be, base would be 2d and the angle is phi, so it would be 2d cos of phi. So it is proportional to 2d cos of phi, and I will be removing the proportionality constant. I can represent it as 2 beta d cos of phi, which is 2 psi. Similarly, antenna 4 leads antenna 1 by 3 psi. Similarly, antenna N leads antenna 1 by N minus 1 psi. So I can represent the total electric field as E naught for antenna 1, E naught e raised to power j psi for antenna 2, E naught e raised to power 2 j psi for antenna C, and similarly E naught e raised to power N minus 1 j psi for antenna N. So I can take the E naught common and I will be having E is equal to E naught 1 plus E raised to power j psi plus E raised to power 2 j psi plus so on plus e raised to power n minus 1 j psi. If I multiply with e raised to power j psi on both of the sides, I will be having e raised to power j psi as e naught e raised to power j psi 1 plus e raised to power j psi plus e raised to power 2 j psi plus so on e raised to power n minus 1 j psi. Now if I am taking this e raised to power j psi inside, I will be having e naught e raised to power j psi plus e raised to power 2 j psi. I am just increasing the power of the e raised to power j psi. So here if it was e raised to power j psi, I will be having e raised to power 2 j psi, and so on e raised to power n j psi. So I am going to subtract 2 from the first. This is my second equation, this is my first equation. So e minus e raised to power j psi will be equal to e naught 1 plus e raised to power j psi plus e raised to power 2 j psi plus so on e raised to power n minus j psi minus e naught e raised to power j psi plus e raised to power 2 j psi plus so on e raised to power n j psi. So all of them are going to cancel out. I am left out with e common 1 minus e raised to power j psi here. I am going to take e naught common and I am left out with 1 and e raised to power n j psi only. Rest all of the term are going to cancel out. So e naught 1 minus e raised to power n j psi. So I will be getting e raised to power j psi by 2 common from here and e raised to power n j psi by 2 common from this side. So I will be having e raised to power j psi by 2, e raised to power minus j psi by 2 minus e raised to power j psi by 2. Here e naught e raised to power n j psi by 2, e raised to power minus n j psi by 2 minus e raised to power n j psi by 2. Now this is the formula of 2j sine of theta, right? So if e raised to power j psi by 2 multiplied with 2j sine of sine by 2, it will be equal to e naught e raised to power n j psi by 2, 2j sine nj psi by 2. So 2j and 2j will get cancelled out and E will be equal to E naught sine nj psi by 2 upon sine psi by 2. E raised to power nj psi by 2 minus j psi by 2. This is the phase. Actually, if I take the reference at the center, this phase is going to become 0. So I can represent the phase as angle. So E will be equal to E naught sine n psi by 2 upon sine psi by 2 angle and minus 1 psi by 2. Right, so array factor will be equal to E upon E max. So maximum electric field will be equal to, so I am going to find out with the help of the limits. Okay, so I am going to find out E max as n E naught. So when I am dividing it with n E naught, array factor is going to coming out as sine n psi by 2 upon n psi by 2. Okay, so I am going to take sine theta is nearly equal to theta when theta is very less. So in that case, sine theta is nearly equal to theta. So only this assumption is used and the array factor will be sine n psi by 2 upon n psi by 2. So I hope you understood this experiment and I hope you are going to meet me soon in the next lecture. Thank you so much.